Okay, in this video we're going to talk about atom notation, isotopes, and we're going to try a couple of problems to put everything together. To be honest with you, this wasn't a section that I found the most interesting while learning it, but we'll try to make it as quick and easy as possible. Atom notation is just a fancy, shorthand way of explaining three qualities about an atom: what element it belongs to, how many protons it has, and its mass. Let's pick an atom, say oxygen. This atom's element is, well, oxygen, and because oxygen has 6 letters and that's way too long, we're going to abbreviate it into its chemical symbol. Oh, 1 letter. Very easy. Let's write this down real quick. Next, we want to know how many protons oxygen has. Each element has a unique number of protons, and this number is equal to its atomic number on the periodic table. Oxygen is the 8th element, so it must have 8 protons. Hydrogen would have 1, helium 2, lithium 3, and so on. We're going to take the atomic number and write it to the bottom left of the O, like this. Now we know we're talking about oxygen, and oxygen has 8 protons. Finally, we're going to look at this atom's mass. Let's say that this atom of oxygen has a mass of 16 atomic mass units. We're going to take this number and write it to the top left of the O, like this. Now we have our complete atom notation. The big letter represents the atomic or chemical symbol of whatever atom it is that we're talking about. The small number to the bottom left is the number of protons that this atom has. The small number at the top left is the mass of the atom in atomic mass units. Each element has a unique number of protons anyway, so the element and the number of protons are kind of telling us the same thing. For this reason, the atomic number is often omitted from atom notation. If we generalize this notation, X represents the unknown atomic symbol, A the mass number, and Z the atomic number. We can actually take the information that atom notation gives us and do some quick calculations to figure out a third value. Recall that protons and neutrons each have a mass of 1 AMU, and that electrons are essentially massless. Since we have the total mass of the atom and the number of protons that are in the atom, we can use this to figure out the number of neutrons that are also in this atom. Going back to oxygen, we know that this particular atom of oxygen has a mass of 16 AMU and 8 protons. 8 protons at 1 AMU each gives us 8 AMU. 16, the total mass, minus 8 AMU, the mass of the protons, gives us 8 AMU. 8 AMU divided by 1 neutron per AMU gives us 8 neutrons. So we know that this atom of oxygen has 8 neutrons, 8 protons, and a total mass of 16 AMU. Just for fun, let's look at a couple of different examples. Even if you think this looks way too easy, humor me and just try a couple. For example, if we look at this atom of chlorine, we know that it has a mass of 35 daltons and has 17 protons. 35 minus 17 gives us 18. And so we know that this atom of chlorine must have 18 neutrons. Next, let's look at this atom of nitrogen. It has an atomic number of 7 and has 8 neutrons. What's its total mass? Well, we can add up the mass of the neutrons plus the mass of the protons, which gives us 8 plus 7, which equals 15. One thing that I kept forgetting personally about atom notation is that it only describes a single specific atom and is not a generalizable descriptor of all atoms of that element. The atomic symbol and number of protons is always the same for every atom within the same element, but the mass number can change. Since the number of protons is fixed for a given element and electrons is essentially massless, what do you think might be contributing to the variable mass? That's right, the number of neutrons. Atoms of the same element can have a different number of neutrons and therefore a different mass. These are called isotopes. For example, titanium can exist with mass numbers of 46, 47, 48, 49, and 50. With an atomic number of 22, we know that this corresponds to 24, 5, 6, 7, and 28 neutrons, respectively. These are all referred to as isotopes of titanium. When we refer to an isotope of an element, we add the atomic mass of that element after we say the name of the element. For example, if we have an isotope of titanium with a mass of 50, we would refer to this isotope as titanium 50. The last thing to know about isotopes is that although their masses are different, chemically they behave virtually identically. The last thing to think about is how to find the average mass number of a tub full of atoms of the same element. We're going to use a little bit of math to figure out a weighted average. Now, if you're already really comfortable with weighted averages, feel free to skip this part and go ahead. But if you need a little bit of a refresher, like I do, stick around. Let's say that we have 2 types of ice cream, pistachio and Oreo. We have 1 scoop of Oreo and 1 scoop of pistachio all mixed together into a sundae. We know that 1 scoop of Oreo ice cream weighs 10 grams. 1 scoop of pistachio weighs 15. Let's say that we take a scoop-sized bite out of the sundae. how much would this average scoop weigh? Well, we know we have 1 scoop of each and that the sundae is made up of 2 scoops total. So the whole sundae must be half Oreo and half pistachio. This proportion stays the same, so we know that our scoop size bite is also going to be half Oreo and half pistachio. That is, half of the scoop will be 10 grams a scoop and half of the scoop will be 15 grams a scoop. If we do some math here, 10 grams a scoop of Oreo times half a scoop of Oreo gives us 5 grams. 15 grams per scoop of pistachio times half a scoop of pistachio gives us 7.5 grams. 5 grams plus 7.5 grams gives us 12.5 grams. Now, let's imagine that instead of 1 and 1, we have 2 scoops of Oreo and 3 scoops of pistachio. We take another scoop size bite. How much would it weigh? This time we know that the sundae is made of 5 scoops total, 2 Oreo and 3 pistachio. So a scoop size bite must maintain the same proportions. That is 2/5 Oreo and 3/5 pistachio. If we do the math here, 10 grams a scoop times 2/5 of a scoop gives us 4 grams of Oreo. 15 grams a scoop times 3/5 of a scoop gives us 9 grams. We add those values together and our weighted average is 13 grams. These are both examples of weighted averages. Now let's apply it to isotopes. Suppose we had a sample of carbon. We're going to switch out the ice cream scoop fractions for percentages and the scoop mass in grams for atomic mass units. Let's say the sample is 2/5 or 40% carbon-12 and 3/5 or 60% carbon-14. What is the average atomic mass of a carbon atom in this sample? Think of this as though the average carbon atom is like a scoop that we're taking out of the ice cream, and that is composed of 40% carbon-12 and 60% carbon-14, the same proportions that make up the entire mixture. This atom is 2 out of 5 or 40% C12. 0.4 C12 times 12 AMU per C12 gives us 4.8. The average atom is 60% or 3/5 C14. 0.6 carbon-14 times 14 AMU per carbon-14 gives us 8.4 AMU. We add up those two masses and we get 13.2 AMU. The average atomic mass of a carbon atom in this sample is 13.2 AMU. We can generalize this thought process into a formula. We take the mass of an isotope in a sample times the proportion that that sample adds up. We repeat this process for every single different kind of isotope in that collection. Then we add up all of those numbers, and that gives us our average atomic mass. Finally, imagine that our sample size was all of the silicon atoms on Earth in the following proportions. What is the average atomic mass of a silicon atom? Take a second to see if you can figure it out. If it were me, I would definitely think to myself, yeah, I can figure this out, this is super easy, and then realize when I got to the test that I actually had no idea how to do it and screw the whole thing up. You guys are probably smarter than me, but take a second and see if you can figure it out. The average atomic mass is 28.1 daltons. If we check the periodic table of elements, we can see that this aligns pretty closely with the 28.09 daltons that's labeled there. Atomic masses on the periodic table of elements are a weighted average that take into account every single naturally occurring isotope and their fractional abundance on Earth. Lots of stuff was covered here, so quick review. Atom notation covers which 3 qualities of the atom? That's right, it's atomic symbol, atomic number, and atomic mass. What extra value can we figure out from atom notation, and how do we do it? That's the number of neutrons that we can figure out, and it's the atomic mass minus the atomic number. What are atoms of the same element with different masses called, and what makes their masses different? They're called isotopes, and neutrons are responsible for that mass difference. And finally, how do we figure out the average atomic mass for isotopes in a sample? We take a weighted average. That is the sum of the products of the isotopic mass and the fractional abundance of an isotope for each isotope in that sample. Hopefully this was helpful. If there was anything that didn't make sense or could have been explained better, please let me know in the comments below. I'd love to hear your thoughts, and that's how these videos keep getting better. Thanks for watching.